The only known analog to me is the work of Ivanov, Davidson, and Korovkin. We're going to compare with that. And then I'm going to show you some pictures. So requests for quotations. These are first price sealed bid procurement auctions, typically pretty small, with reserve price being not bigger than around $8,000. And this is a typical timeline. So at some point, the auction has to be announced with a reserve price, and then participants have some time, typically a week, to submit their bids. In this example, two bidders submit their bids. The first bidder wins because it's the lowest bid. But now imagine this happens. Right at the end of the auctions, minutes before deadline, comes the third bidder and bids just below the previous winner. So this is kind of suspicious, right? It's almost like this third participant was waiting until the end of the auction so that everybody else make the bids and submits his bid, having this information about other participants. So this is illegal, yeah. And this is called bid leakage. This is what we're trying to detect. And this also might be coincidence, right? This might be a perfectly honest bidder. So we can't say that this is 100% unfair participant. We can only say that there is some probability. And this probability also changes if we move this bidder to the left or to the right or adjust his bid. So what we need to do is to map his bid to a probability that he's corrupted. So basically it's a classifier, right, that we need to build. So I want to emphasize these three patterns of bid leakage, like three kinds of traces that bid leakage leaves in the data. So one is undercutting, when the winner wins by a very small margin, and the other two are that the bidder tries to grasp all the other bids, so the bidder bids in the end, the unfair bidder, and tries to bid last. And these are formulated by Ivanov, Korovkin, and Davidson. So it's probably also that all these three patterns has to be in place in order to say that, yeah. No, so in this first price sealed bid auction, every participant submits only one bid without any information about anyone else. Yeah, so we can probably say that the auction is not suspicious if only one of these patterns is there, right? If a participant bids a buck before the second place, but right at the beginning of the auction, it's probably not bid leakage, right? So there is some nonlinearity here already. So these are going to be our features. On the next slide, the data set. We have initially 1.4 million auctions over a span of 4 years. These are open access, Russian procurement auctions. Every auction has to be there. We drop more than half of it, some due to errors in the data, and others are the auctions with one participant, and we cannot apply our methods to these auctions because we basically compare winners and runner-ups, and auctions with one participant have only winners, right? And here are some of our features. There's two more, actually, I just skipped them. So the first three are what we've seen already, right? Undercutting, bid timing, and whether a participant bid last, which are supposed to reflect bid leakage. And also one feature we use is that whether a participant participated before in an auction with this procurer, which might mean something or might not. So these are the features. What's the model? As I said, the main problem is that data is unlabeled with bid leakage. We cannot just train a classifier on these features, even though we would like to. But what we have instead is a noisy label of corruption, and that is winning in an auction. What do I mean by that? What we assume is that every participant that did not win in an auction is a fair participant. So it's either that, or this participant lost even though he had unfair advantage. So he's just, we're not interested in this loser. So we're only interested in winners. So kind of runner-ups, second places we don't study yet. Others are fair, and winners are a mixture of fair and corrupted participants. So this is kind of a noisy label. And then if we classify winners and versus runner-ups, then we also obtain a biased classifier of corrupted versus fair. And we will need to unbias that. So a quick note about this assumption. Well, first, we kind of find evidence that it seems like it holds about that runner-ups are fair. But also, this assumption, if it doesn't hold, it leads to kind of conservative error that we find less when there is, which we're kind of fine with. So all we find is actually there. Yeah, the features, you've seen them already. The core idea of the feature design is very important, that the features has to be as close as possible to being irrelevant in fair auctions, so that the classifier that we built that classifies winners and runner-ups only classifies them due to corruption, not due to natural reasons. Now this is actually unachievable, but we try to get close to that. And we'll also then make a placebo adjustment to account for that not being true later. And the classifier is XGBoost. Yeah. So any questions so far about this? This is just a part of our methodology, the winners classifier. Well, here's kind of the third bullet point that no. Yeah, so we assume that no, but as I said, it leads to conservative mistakes. And we also kind of have evidence that it actually holds, more or less. Yeah?
So imagine that instead of the auctioneer telling me someone else's bid, I was just very good at spying on the other bidders. Would that show me up as corrupted in your classification?
Yes. So we assume that the bidder, the procurer leaks the bid, but yeah. And if you have a friend who told you and you betrayed him, yeah, that will also be corruption. Okay, so this is the classifier. To understand the full methodology, so we need to unbias this, right? This is just a winners classifier. It's not corruption classifier. So to grasp the full methodology is kind of hard, so I just present a high-level intuition, sort of. And we take a step back from the classifier, and we look at one feature right now. So this feature is timing of the bid. And you can play a minigame, find corruption in this picture. So the y-axis is probability density function. The x-axis is bid timing in minutes until deadline. So on the right, it's about 24 hours before the deadline, and on the left, 0 is the deadline of an auction. And we have two probability density function. The red one is for winners, and the blue one is for runner-ups. So let's start from the right. There's some activity on the right the day before the deadline. Then there's night, so everybody's asleep, so there's no activity. And then on the left, there's a huge spike of activity, right, in few hours before the auction. But notice that while both winners and runner-ups are very active, the winners are more active, right? So there's some excess of red over blue there on the left, you see? And we basically say that this excess is due to corruption. Right now, we will correct that a little bit later. Yeah, so we basically say that if there was no corruption in the data, then the red and the blue would be exactly the same. But since there is some corruption, the red ones are more active at the end. Well, because it's their strategy, it's corrupted bidders. So we're going to relax that on the next slide, basically. Yeah, and then this is just one feature. But we use 6 features, and we might want to use more. And then if you use 6 features, it's not that easy to just estimate the probability density function because of cursive dimensionality. And that is why we need the classifier, because classifier conveniently aggregates all the features that we have into one dimension of a predicted probability by this classifier. So actually, when we use this method, we don't estimate the density of every feature, we just estimate the densities of classifiers' predictions, which are one-dimensional, which is convenient. So it's a similar picture, but for different kind of thing. And what we do next is, well, we estimate these densities of predictions, and we apply the bias rule. Since we have this probability density function, we can apply a bias rule to estimate the probability of corruption. And that's the whole kind of pipeline. Okay, questions about this? No, this can be a little muddy. Okay. Well, don't worry if you didn't get this. So the next thing is placebo auctions. It's a very simple thing. Why do we need them? So here we basically assume that fair participants don't differ at all. So fair first places in fair auctions and second places in fair auctions, they don't differ at all in all the features that we use. That's kind of a bold assumption, and we want to relax that. And to do that, we use these placebo auctions. So placebo auctions is very easy. We just drop winners from the real auctions in the real data set, and we declare that now the second place is the winner and the third place is the runner-up. And here we have this new synthetic data set of auctions, which are fair now because we dropped all the winners who are the only guys who could be corrupted. So these are fair auctions. Okay, and this is kind of an example from the previous example of corrupted auction. Here we have third bid thrown away because it's a winner. And we have now an auction with two participants. The first one wins, and it's a fair auction. And this is the data set of these auctions. And the idea is that if we apply our whole method to this kind of placebo auctions, and we find that some auctions are corrupted, then our method is obviously positively biased because these are fair auctions. And then we need to correct our method. And how do they do that? So here's the previous picture. And what we assume there is what we would call independence, which means that winners don't differ from runner-ups in fair auctions. But can we test this assumption? Well, kind of. So what if we draw the same picture for third places? In case of independence, we would expect that it would be very similar to blue line. So let's do that. And it's actually similar, but not quite, right? If you look at the left, then again, there is some excess of blue over green. And that is because even in fair auctions, participants differ. So the reasons in a few seconds. So how this changes our method? Well, we don't assume independence, we assume now what we call parity, which is that winners do differ from runner-ups, but the same way as runner-ups differ from third places. And so if you look at the picture at that left top part, it means that not all the excess of red over blue is due to corruption, but only that part of it that cannot be explained with excess of blue over green. So in other words, the difference of red and blue can be due to either corruption or due to fair natural reasons, and we divide those. Yeah, so what's the reason of this strange behavior? It can seem kind of counterintuitive that in sealed bid first prize auctions, timing actually affects your chances of winning in an auction or taking second place over the third one. This is kind of nuts. So there are actually a few reasons. One is that not the corruption, but expectation of corruption changes the picture. So imagine you're a participant and you expect that someone is going to try to steal your bid. Well, you're going to try to beat even after him, right? So even closer to the deadline. So the unfair participant doesn't have time to steal your bid. And maybe the more experienced participants, they know about this, but the naive participants don't. So the naive take third places and they don't bid as close to the deadline. But there are actually perfectly natural reasons for this too. Even without corruption, this might happen because, say, you as a fair participant, you don't really care about an auction, so it just comes out, you submit a bid, you forget about it. But if you really care about it, then you carefully evaluate your value function to know exactly what you want to bid, and then you bid later than this participant who doesn't care. And then you also bid, probably win more often because you care more. So, okay, there are some reasons for this behavior anyway. Yeah, and that's how we use placebo. Any questions about the placebo? Yep. Technically, it's the following. The differences of probability density function of fair first and second places, or rather of fair first and second places in real auction is the same as that in placebo auctions. So it's the difference of probability density function that is the same. It's absolutely not ratio. The problem with ratio is that if you do that with ratio, then it stops being a probability function, basically. So you find ratio of blue over green, and then you multiply it to get red, and then red is not a probability density function anymore, basically. Because it has to sum up to 1, and it doesn't anymore. Yeah. Other questions? Yeah? Yeah, we do kind of a thing like that. When we test parity and independence, what we find is that independence definitely doesn't hold, and that parity kind of holds. But yeah, the difference between red and blue and green is definitely significant. Yeah. Something else? Okay. Yeah. Yeah. So. Yeah, I agree. So the fact that we don't have labeled data, it presents us scientific challenges, but it's also a curse because we can't validate, right? That's pretty bad. We don't. So what we do is first we try to verify the assumptions that we can, and that we cannot, we try to assume so that we have conservative estimates, so it's not less than none less corruption than that. And what we also try to do is synthetic data, so that it's not in the paper actually. So we just make some fair auctions and some corrupted auctions, some fair auctions are just permutations of real data set, and corrupted auctions are what we assume the corruption would look like. Like they beat at the end, they beat just below the winner. And then when we train classifier on this real data and apply it to this synthetic data, which I just described, then it works really well, which is kind of also a point that everything's correct. But yeah, we don't have validate. Yeah. Okay, so what I have left is comparison with the other paper. So one comparison is that we use this fairly complicated machine learning technique, and they use some simple statistics, and they can also only estimate prior probability of bit leakage using only one feature. And what we do is we also estimate posterior probability of bit leakage, so that we know that this auction is corrupted with this probability. And we can use any amount of features, basically. And the other thing is this difference of independence versus parity assumptions. So by using placebo data, we can assume disparity, and this makes our estimates about 30% smaller, which is a huge difference. So, and we also have seen that independence probably doesn't hold. Yeah, and what I have now is some pictures. So we find that 16% of auctions is corrupted according to our conservative estimates. And here are some pictures to how this probability depends on some auction characteristics. For example, top left is dependence on reserve price, so the maximal price of auction. It makes perfect sense that the correlation is positive, because the more money there is in auction, the more money there is to steal, right? The more inclined are people to engage into this kind of corruption. And here is a map of Russia colored with respect to corruption in each region. And we see that on the south left, southwest, there's the most corruption. There's also a lot in central cities, Moscow and St. Petersburg. So this is it. What? Oh, Sochi Olympics. Yeah, it's there. Yeah. Are you surprised? Okay, thank you a lot.